All right, so we're going to have two lessons in one on Eulers Method, which is a very important topic that is tested frequently on the BC exam. Multiple questions each exam on it. Usually one multiple choice or two multiple choice, and then one part of a free response. And then the logistic differential equations, usually we'll have one question on that somewhere in the test. Guaranteed. We're not going to focus too much on it though. We could really dive deep into this lesson, but I'm not going to. I think it's a waste of time. So let's start with talking about Eulers Method. I need to copy this over. Okay, let's remember from the first semester, one of the last lessons was using tangent lines to approximate values. Let's remember this. Like, let's approximate the square root of 17. Okay? Well, I have the function y equals the square root of x, and I know the square root of 16 is 4. What I could do is create a tangent line at this location, and using a tangent lines equation, I can find this value here on my tangent line that would approximate my actual value of the square root of 17. Right? How do we do that? Well, we would say, okay, we're going to use f of x equals root x, and the fact that we know f of 16 is equal to 4. Now I'm going to write my equation of my tangent line. Remember, equation of a tangent line, we have y minus y1. We have the point times m times x minus x1. I should have put 4 here. That's my y coordinate. And then what goes there, and how do I find it? For my tangent line equation. This is a nice little review. Yeah, it's the slope of the tangent line. How do we find the slope of tangent lines? We use derivatives. So this is going to be f prime of 16. Well, let's recall how to find the derivative. We've been taking integrals a lot. Well, not here. We've kind of gone away from everything, derivatives and integrals, but we're back now. We use the power rule, bring down the 1/2, subtract 1. We get that f prime is 1 over 2x. I can plug in 16. F prime of 16 is equal to 1 over 2 root 16. So that's 1/8. So that's the equation of that red line right there. Okay? Well, instead of trying to calculate the square root of 17, which I don't know, I can approximate f of 17 using this. Now, again, I'm approximating f of 17. The x value is 17. I plug in 17 to get the root of 17, but the x value is 17. So what I will do is I'll say y minus 4 is equal to 1/8 17 minus 16. Or f of 17, which is the square root of 17, is approximately 1/8 times 1 plus 4. And in my calculator, go ahead and plug in 4 plus 1/8 and see what it equals. And then plug in the square root of 17 and see what it actually equals. Using a tangent line, we say that the square root of 17 is approximately 4.125. The square root of 17 is 4.123. Fantastic. This is a very good approximation. Okay, so tangent lines are very powerful. And why are tangent lines powerful? Well, because if we zoom in at a location, our functions end up looking like lines. They look linearized if you think about it. Okay, you zoom in here, and if I zoomed in there, all I would see is just a line with a red line on top of it. And that red line's the tangent line. The tangent line, isn't exactly on top of it, but is very, very close to it at locations. Right? But it's got some drawbacks. What happens if we use the square root of 16 to approximate the square root of 18, or the square root of 19, or the square root of 20, using a tangent line? Discuss with your neighbors. What happens? What's the problem? Do we have problems, or are we good? What do you think, Miss Woolley? Yeah. The further away we get from the actual point, the less accurate we're going to be. Okay? So the idea is if we use just one line, and also if we end up having a curve that increases really quickly, and we're using a tangent line that's down here, well, since we're increasing really quickly and we're using our tangent line, we could be way, way off with our approximation. Okay, so the further away we are, the less accurate we are, and also depending on how quickly your function's increasing or decreasing, we also could lose some accuracy there. Okay, so tangent line's great, but don't go too crazy with them. Well, we got this guy, Leonard Euler, nicknamed Lenny. He says, hey, hold on, guys. Why stop at using one line? Why not use multiple lines? He actually said, let's use multiple lines. Okay? So what he said is, hey, if this is a tangent line, and we want to approximate this, well, I'm going to be way off, right? This tangent line is going to go all the way up here, and my approximation is going to be, so far away. So he said, no, let's not just use one tangent line to cover this. Let's split this into a couple steps, say 3 steps. They're just equal delta x's. They're not dx because they're not an instantaneous change. They're delta x's because they are an overall change. And he said, don't try to approximate this value with the one tangent line. Instead, do approximations one step at a time. And after you do your approximation, pretend like that point is on your curve, and then go from there to your next point, and from there to your next point. Okay, so let me show you what that looks like. He instead says, okay, use this point, which is over my first step. I don't want to go crazy here, so let's just kind of make it look a little nicer. Okay, so my first step brought me here. And then he says, okay, well, if this was on the line, we would have a tangent slope that would be like that. So what he says is create what essentially is another tangent line right there. Now notice we're going off of this point, which isn't on my function, but I'm pretending like it is so that I know what slope to use. Okay? And then he says, okay, there's your first step. Now we go to our second step. Let's take it right there. And he says, use this tangent line to approximate this value. Fantastic. And then he says, okay, we got one more step. So let's look at this tangent slope right here. It's like that. So I will create another tangent line, pretending like it's on that line. And I will use that final tangent line to approximate my function value. Okay? Use multiple tangent lines to increase the accuracy of your approximation. I'll put tangent in quotations because we see this line is not tangent to this function. It is located at a different point. However, the slope is the same slope of this line, is the same slope as this tangent line. Use multiple tangent lines for a better approximation. Okay? I think that's a hat. Looks like he's got a lazy eye too. That's why he's facing that way. I don't know. Okay? Here's the steps we're going to take. First, you got to figure out where you're starting and what you're approximating. You got to figure out how far that distance is. Then you're going to figure out how many lines you're going to use or how many steps that you're taking. You may be told how many steps to take or what a step size is. Steps will be the lines. Step size will be the delta x, and you can use your delta x to figure out how many lines to get from one location to the other. We're going to use the point generated each step along the way in our next approximation. We're going to assume that that point that I generate is on the original function to find its slope of its line. Okay? And all it is this picture. Keep this picture in your head where you have tangent lines to get my slopes of these lines so that I can go 1, 2, 3 steps to get a more accurate approximation instead of just using my first one, which would have been way, way off. Okay? So let's do an example. This is not a practical example because we're going to have to use our calculator. If you're using your calculator, you might as well just type in what the value is. But for a visual example of something that we've already done, here we go. Approximate the square root of 17 using Eulers method with a step size of 0.5. Now, I'm not going to tell you in future questions that that means you're taking 2 steps, so you're going to use 2 lines, okay? And I want us to compare to our original approximation of root 17. Okay? If you want to draw a picture, you can. Sometimes it helps. Got the square root function. I'm going to use, again, a point, an initial condition that I know. So I'm going to use y equals f of x, well, f of x is equal to root x as my function. And I know that f of 16 is equal to 4. Now, instead of just using one tangent line, we're going to go from 16 to 16.5 with one tangent line. And then we're going to stop, and we're going to produce a point. We are going to assume that point is on my function, and we're going to look at the slope of the tangent to my function at 16.5. What that enables us to do is kind of shallow out my next step so that after my next step, I would be closer in terms of my approximation to my first approximation, which just used one tangent line. Man, draw a straight line. Sure, whatever. Okay? Okay, so we're just going to go one step at a time. We are going to use the point 16.4, my xy, and the fact that f prime was equal to 1 over 2 root x. So f prime of 4 was 1 over 2 times root 16, that's 1/8, to approximate not 17, but f of 16.5. So I'm going to go and approximate my value at 16.5. Okay? So first I write my equation of my tangent line, y minus 4 is equal to 1/8 x minus 16. And then I could say f of 16.5 would be approximately 1/8 16.5 minus 16 plus 4. That's 1/8 times a half, which is 1/16. So this is 4 and a 16th. I'll just leave it as 4 and a 16th instead of simplifying it. Well, whatever. Let's simplify it. 65 16ths. Okay? We're halfway there. Now we use this point. We say this point is 16.5, comma, 65 16ths. So I'm going to say assume we have 16.5 and 65 16ths is on my curve. I'm going to assume that that's on my curve so that when I find the derivative or the slope of the tangent here, I will use the derivative of my original function where it actually is located at 16.5. Now that means I have to plug in 16.5 into 1 over 2 root x. That's not something we can do by hand. So again, this is not a practical example. In the future, we will be able to do these questions by hand. But let's just whatever. I'm going to just write it out. So I'd have 1 over 2 root 16.5. That's my derivative. That gives me, let's just write this down. This was the equation of the red line right here. Now I'll change this to blue. Here comes the equation of the blue line. Y minus (65 16ths) equals 1 over 2 root 16.5 x minus 16.5. Okay. We will use this to approximate f of 17. So I'd say f of 17 is approximately 1 over 2 root 16.5 times 17 minus 16.5 plus 65/16. Go ahead and type that in your calculator, and I guarantee that it will be a closer approximation than 4.125, which was our original approximation. But it is. And we could talk about what we could do to get even better approximations. Yes, exactly. We could take more steps. We could take smaller step sizes. We could use more lines so that we'd have lines essentially mimicking my curve at a lot of points, and boom, we'd have better approximations the more steps we take, right? How close are we? Okay, that's good. So root 17. Hey, you got to do what you got to do here. Okay, we had 4 and an 8 was our first approximation, right? Okay, so 1 over, in parentheses, 2 root 16.5 times 0.5 plus 65/16. Good. Look at 4.124. That's closer than 4.125, right? Fantastic. Okay. Now, understand more steps, smaller step size, better approximation. Okay. Let's do this one. Do we want to do this one? Let's move on. We could do this one, but more practical applications of Eulers' method is to find potential solutions to differential equations. Certain differential equations like dy dx is equal to 2x plus y, you all do not know how to solve this differential equation. We think, oh, you could just separate your variables, subtract the y, multiply by dx. But think about that. If I subtract the y and then multiply by the dx, I'd have dx on both sides. You can't separate variables if we have addition. Okay, so we need an alternate method to solve this differential equation. Well, we're not going to solve it. Instead, we're going to approximate the solution using Eulers' method. This is telling me what the slopes of my tangents are going to be. Okay? I don't know what my solution looks like. I don't know what the curve looks like. But I have a point. And I know what the slopes are at any point. What I will do is try to find my solution at x equals 2 using this method, which will take me from a straight line to another straight line to approximate a solution. Okay? So let's use Euler's method with 2 steps of equal length to approximate f of 2, knowing dy dx and the point 1, 0. Okay, I'll do this one. You'll be able to do the other one, no problem. Okay, so I'm going to first start with 1, 0 and dy dx at 1, 0, which is 2, to get my equation of my first tangent line. Y minus 0 is equal to 2, x minus 1. And I'll use this to approximate What? Very good, and I kind of skimmed over that. We know we have the point 1, 0. Well, I'm going to approximate whatever the y value is above 2, but I'm taking 2 steps with equal length, so that means I need to divide this distance of 1 by 2. So I go from 1 to 1.5, and I go 1.5 to 2. Maybe like that, maybe it actually increases. I don't know. If your function looks like that, then maybe you're shallow to steeper. Who knows? Okay? So 1.5 is what I'm going to approximate. Okay? So f of 1.5 is approximately 2 times 1.5 minus 1 plus 0, which is just 1. So, boom. 1. So now I have the point 1.51. I'm going to assume 1.51 is on my solution to my differential equation. So I'm going to find its derivative if it was on my equation. So I will be able to plug in dy dx at 1.51. Though we know this isn't on the solution, we are assuming it is to get its slope of its line to get us a better approximation. 2 times 3/2 is 3, plus 1 is 4. That gives me y minus 1 is equal to 4 times x minus 1.5. This is my second line here. But the slope is steeper, so we're actually going up more, like that. Okay? We will use that to approximate f of 2. F of 2 is approximately 4 times 2 minus 1.5. You will notice that in here will always be our step size. So you don't have to write this repeatedly if you just know it's going to be 0.5 every time. Plus 1. 4 times 0.5 is 2. 2 plus 1 is 3. Okay? We think that we will get up to 3, and an approximation for my solution is 3. Questions? Fantastic. Do this one. No. Sometimes it'll be 3 steps. Sometimes it'll be 4 steps. The more steps, the more annoying, because the more tangent equations you have. Now, how the book teaches this and how most people teach this is, you can kind of come up with a formula, and there's like a table method where it's like, oh, use this and then add this, and then boom, 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 boom. But I know there's a lot of stuff to remember for the BC exam. I don't want you to remember formulas and how to do tables. I want you to remember more of like the ideas and the thought process behind it. I find it's easier to remember, oh, we're just using multiple tangent lines than anything else. Because you guys can apply this to your regular tangent line approximations. It's not a one-off lesson. It's just an addition to a tangent line approximation lesson. Go, give it a shot. You can use your calculator for the calculations if it helps. You actually will be required to probably do this without a calculator. So multiplying decimals, multiply normally, move the decimal place over twice, and then 1.6 minus 0.36. Turn that into 1.60. This turns into a 5, 10, 4, 2, 1.24. But it's negative because it's 0.36 minus 1.6. And I look up and hope and pray and see my answer. Whoa, look at that. Yellow and pink turns to red. Okay? Sometimes you'll see the problems in a table like this. Actually makes things a little bit easier. Let's go ahead and tackle this. This is a 3-step. Look at that. It's more than 2 steps. Does it ever go to 4 steps? I've seen it once, I feel like. I don't know. Just to be cruel. Usually max is 3 steps. Min is 2 steps, you know? Like, that's it. Because we don't have that much time to do these problems. My method may be a little bit slower than another method. But my method, I feel like, is more reliable because students will remember it. Okay? Just use multiple tangent lines. Assume each approximation is on the function. So you're using the function's derivative to find your next tangent line. 1.34 plus 1.4 is 1.74. Anybody else get that? Okay. Okay. Eulers method. Just think of old Lenny Euler saying use multiple lines, okay? And you'll be okay. To the other lesson, this one being the more important of the two. We're going to talk about logistic differential equations. It's actually not very calculus intense, but you have to just be familiar with it. Now first, something that we need to talk about is something that exponentially grows or decays. Okay? Exponential growth, if this is a population, say, P of T, okay, we can write a differential equation for this situation. We can say that the change in my population with respect to time is relative to its own size. So it's depending on the population size multiplied by some constant, we would get the differential equation for something that grows exponentially quickly, or slow, or something that decays exponentially quickly. Okay, so if you ever see something like this, like dp dt is equal to 5p, or w, dw dt is equal to 2w, you know that you have an exponential growth situation. And when you solve this differential equation, you get this familiar formula. And we could do this if we had time, but we don't have time. P equals C e to the kt. This is the solution. Where have you seen that before? Well, you've probably seen PERT before. There's usually something here. This is like an initial. PERT, right? Okay, this is your solution for a exponential growth model. Okay, sometimes we'd use this. There are certain problems in the past that have done this, but really for you guys, it's important to just understand this is your differential equation for something that grows exponentially quickly or slowly. If k was negative, we would have an exponential decay, which would look something like that. Great. Well, we actually move past these types of problems. And we say, you know what, exponential growth is not very realistic in most applications in the world. Sometimes populations do not grow exponentially. It won't always, exponentially grow and take over the world. There might be a limited amount of resources available so that there is a cap on your total population. And this is something called logistic growth, okay? Where our population, and it might be important for me to show you the graph again, where the population will look like it's growing exponentially, but then all of a sudden something happens out there in the world, and all of a sudden we start going slower and slower and slower until we reach some limit where it's like we can't grow anymore or else we'll all die, or we'll just go back to the limit. Okay? Does that make sense? When does this occur? In nature, if there is only enough food for a certain amount of animals due to predator-prey kind of relationships, we can't have an infinite amount of lions out there because eventually the antelopes will all run out. Okay? Now, we call the limit L our carrying capacity. This is a very important term, the carrying capacity. This is the max population you could have. the population, it's what your population will trend towards, but will not exceed. Okay? The equation for this differential equation is K times P, which is familiar to exponential growth, only the limit comes with this L minus P. So we have to multiply it by this, because we can see as P gets closer and closer to L, we'd have L minus L, which goes to 0, and all of a sudden dP dt gets smaller. Now, the solution to this ends up being this. Now, in most BC calculus classes, they go into a lot of word problems using this solution, and they kind of go crazy into it. We are not going to go crazy about it. Okay? We are just going to be able to understand this graph, and if we understand this graph, we're going to be good for any question that we may see. Also, I forgot. Another way to write this differential equation, it won't be with the same K. I'll use something else. We'll say, I don't know, lowercase k. Kp, we can do 1 minus P over L. Okay, as P approaches L, that right side would approach 0, and we end up with this K is just like that K, only we'd have to have it divided by L. It's different, but whatever. We need to be familiar with both of these. And the most important part about both of these is this, L. This is a constant. This is the max population we can have. That's our carrying capacity. Okay? Here's my solution. Most likely we won't have to use it. Just like we won't have to use the solution to the exponential growth decay situation. Important info about the graph of P. Well, we are concave up, and then we flip-flop a concave down. This is a very important point. This is the point at which we are growing at the fastest. So dP dt is at a max at this point. It is also an inflection point. And it can be shown, if we look at the second derivative and solve, that this is at half of your carrying capacity. This is when P equals L over 2. The most important thing. It's where we stop growing exponentially quickly. It looks like we're going to continue on exponential growth, where the derivative is going to increase. All of a sudden, the derivative starts to decrease in values. We go from concave up to concave down. And it's when dP dt is equal to a max. It's also important to know that it does not matter what your initial condition is. You could actually start with a situation where your carrying capacity here is L, and we'd actually could look at something that looks like this, and we trend towards that in the opposite direction. we'd actually probably exponentially decrease, but then go in that. Something like that. Okay? If you remember this and remember that, you should be good. Let me show you the problems that I've seen. A couple of them over the years. This was a 2004 free response problem. It was 4 parts, 2 of which had to deal with logistic differential growth with logistic differential equations. And then the next 2 parts were actually trick questions where they made students think, oh, I have to solve this logistic differential equation, but it wasn't. It was actually a differential equation you can solve using separation of variables. These are the 2 parts on the free response problem that was just logistic differential equation questions. Okay? Part A is if P of 0 is 3, what is the limit as T approaches infinity of P of T? If P of 0 is 20, what is the limit as T approaches infinity of P of T? The important part of here is to find L. L will always be the limit as T approaches infinity of P. All right, look at your graph of what it looks like. We will approach L, no matter how we look at it, if we're above or below. Now, the only way you can find L is to just remember what a logistic differential equation looks like, its general form in terms of its derivative, and then say, oh, L is what? 12. Your answer for part A is 12 for both parts. Part B, if P of 0 is equal to 3. Now this is important because we are, underneath L. So in this situation, if you're underneath L, you go like this. If you are above it, you're going to decay towards it. But if you are underneath L, when is your population growing the fastest? What's this answer? For what value of P? It's not even when. For what value of P is the population growing the fastest? When is dP dt at a max? The same point as my inflection point. At where? L over 2. 6. That's your answer to that one. Okay? Piece of cake. And that was 3 points of a 9-point question. Here's another problem. The function n satisfies the logistic differential equation dn dt. So we're not using p, we're using n, which is equal to n over 10 times 1 minus n over 850, where n of 0 is equal to 1 over 5. It's important to at least know that you are underneath your carrying capacity. Which of the following statements is false? And we have multiple statements. Go ahead and, knowing that L is 850, which means L over 2 is 425, which is the inflection point for n. Which one is false? Compare with your neighbor. I got it. Go ahead. Tell your neighbor the answer. What do you think? Go. Did you get that, Mr. Keneally? You looking at it? It's all about the graph. If you know the graph, you're good, right? Is the limit going to approach the carrying capacity, 850? Yeah, it is. We're good. Is the second derivative 0? Well, yeah, my inflection point's right there. We go from a second derivative that's positive to a second derivative that's negative. We go from concave up to concave down. So that's actually true. When we are greater than 425, what's 425? It's the midpoint right here. Is my first derivative positive? Yes. And the second derivative negative? Yes. Does dn dt have a maximum value at this point? No. We increase at the maximum right here at this midpoint. So B is incorrect. Okay? Final type of question, and a lot of teachers teach this, that you need to know the solution to get this, but it's not true. Not this one. This one is like, which one is a logistic differential equation? This is a legit question on a BC exam. Which of these is a logistic differential equation? Well, you need to see that value y twice, and you know that's a logistic. You shouldn't see any t's anywhere. Remember, it's dp dt is equal to kp l minus p, or 1 minus p over l. Okay, here we go. This question. Number of students in the school have heard a rumor at time t is modeled by the function p. The solution to the logistic differential equation. Okay. At noon, 50 of the school's 500 students have heard the rumor. Also at noon, p is increasing at a rate of 20 students per hour. Which of the following could be the logistic differential equation? Okay. 500 total students, that's my carrying capacity. I should see 500 everywhere for L. So we're good. Well, I need to be able to figure out this value, it appears like. This value is the different value everywhere. That's the K value. Okay? So I know dp dt is equal to some Kp times 500 minus P. We are told at noon, 50 of the school's 500 students have heard the rumor, and P is increasing at a rate of 20 students per hour. This is important because at noon, dB dt is 20, and that's when P is 50. All we do is say 20 equals K times 50 times 450, and we solve for K. And we get this one. That's it for logistic differential equations. Your homework is fairly short. We do a couple practice problems, we quiz. And then you can hang out and get ready for your break. Have a good one.